Okay, so our next problem will involve a diagonalization of a 3 by 3 matrix. The matrix A will be -7, -8, 4. 8, 9, -4, and then 4, 4, -1. So the problem, which are the questions here? Let's find a diagonal for D on a diagonalizing matrix T. Then if we manage to find D and T, that means if the matrix is diagonalizable, then this will imply A equals to T D T inverse. And from this formula, we can calculate basically every function of A. Then the second question will be, let's find an explicit formula for the n power a to the power n. Then it will be easy because we just use a equals to t d t inverse to say a to the power n equals to t d to the power n t inverse. And then it's easy to calculate the nth power of a diagonal matrix by simply raising the power n the entries on a diagonal. And then last, we have to calculate the exponential of AT. And then we'll apply this matrix exponential to find a solution of a system of linear differential equations. So solve the systems. Solve linear system based on the matrix exponential. So basically it's a plan. So let's try to start by writing down the characteristic polynomial and getting the eigenvalues. Okay, so let's see. Determinant of A minus lambda times identity matrix. So -7 minus lambda minus 8, 4, 8, then 9 minus lambda minus 4, 4, 4 minus 1 minus lambda. There's the determinant of A minus lambda times identity matrix 3 by 3. Okay, so let's try to expand along the first row. So this would be -7 minus lambda times the determinant of the 2 by 2 matrix obtained by removing the row in the column of -7 minus lambda. This will be 9 minus lambda minus 4, 4 minus 1 minus lambda. Okay, let's move on to the next entry in the row, which is -8, but this -8 comes with a positional marker of minus. Remember the chessboard with a plus here, then all the signs are calculated accordingly. So the positional marker being a minus, I'll get +8 times the determinant of the matrix obtained by removing the row in the column of -8. So we get 8 minus 4, 4, and minus 1 minus lambda. Okay, and then we keep going. We get +4, the last entry on the row, then +4 times the determinant of the 2 by 2 matrix obtained by removing the row in the column of 4. So 8, 9 minus lambda, 4, 4. Okay, so this will be -7 minus lambda times, so what is this one? Okay, so if you think about multiplying both diagonal elements by -1 to calculate to see better, lambda plus 1 times lambda plus 1 times lambda minus 9, lambda squared -8 lambda minus 9, and then +16 this will be lambda squared minus 8 lambda plus 7. Okay, this will be the determinant. Lambda squared minus 8 lambda plus 7. Okay, plus 8 times if I product on the diagonal elements, we get minus 8 lambda plus 16. Minus 8 lambda plus 16. Then plus 4 times. 8 times 4 is 32. Minus the product of the other two. Minus 36. Minus 4 lambda plus 4 lambda. Okay, so then we get minus 7 minus lambda times lambda squared minus 8 lambda plus 7 plus 8 times 60 minus 8 is 8 minus 8 lambda. 8 times 8 minus 8 lambda plus 4 times 32 minus 36 is minus 4 plus 4 lambda. Okay, so what we get here? Well, let's try to open a parenthesis, so the most straightforward. Minus 7 lambda squared plus, let's do minus 7 first, plus 56 lambda minus 49 minus lambda cubed minus 8, so plus 8 minus lambda cubed, now we look at this one, plus 8 lambda squared minus 7 lambda plus 64 minus 64 lambda minus 16 plus 16 lambda. And this will be, well, let's try to group the like powers. So minus lambda cubed. How many lambda squares we got? Minus 7 lambda squared plus 8 lambda squared. And that's it. So plus lambda squared. Okay, let's count the lambdas now. 56 lambda minus 64 lambda. Okay, minus 7 lambda here plus 16 lambda. So let's do the balance of this. We get 56 lambda with a positive plus 16 lambda, 56 plus 16, 72 lambda. Minus 7 lambda minus 64 lambda is minus 71 lambda. So 72 lambda minus 71 lambda is plus lambda. Okay, now let's do the balance of the three coefficients. Minus 49 minus 16, the minus is minus 49 minus 16 minus 55 plus minus 49 minus 65 minus 49 minus 3 minus 65 plus 64 is minus 1. So the characteristic polynomial is minus lambda cubed plus lambda squared plus lambda minus 1. So equals to 0. This is the characteristic equation. We can factorize minus lambda squared times lambda minus 1 plus lambda minus 1 equals to 0, and lambda minus 1 common factor times 1 minus lambda squared, put a minus here, lambda minus 1 times lambda plus 1, okay, equals to 0. So we got 3 eigenvalues, 2 of them are repeated, so we get lambda 1 equals to lambda 2 equals to 1, and then lambda 3 equals to -1. So after all this messy work, let's try to keep the fruit of the work and erase the work, because otherwise we have too much space on the board. So the eigenvalues are lambda 1 equals to lambda 2 equals to 1, lambda 3 equals to -1. It's not yet clear whether A is diagonalized or not, since we have to find two linear independent eigenvectors for this repeated eigenvalue. So let's see. So what we got first? Lambda 1 equals to lambda 2 equals to 1, and lambda 3 equals to -1. Therefore, D equals to the diagonal. Okay, if it is diagonal, it will be 1, 1, -1, but we don't know yet. So let's try to find eigenvectors. For lambda 1 equals to lambda 2 equals to 1. Basically, we get A V equals to 1V, so A minus 1 times identity equals to times V equals to 0. So basically, subtract 1 from the diagonal element, so -8, 4. I subtracted -1 from -7, I got -8 here. So 8 -4. I subtracted 1 from 9, I got an 8. And then subtract 1 from the lower right corner, so get 4 -2. Multiply by the eigenvector PQR to see what it is, equals to 0, 0, 0. Okay, so let's see. That's, in this case, the equations are highly redundant, actually. So this is the -8p minus -8p minus 8q plus 4r equals to 0. So let's divide by -4. 2p plus 3q minus r equals to 0. That was r equals to 2p plus 2q. That's the first equation. Row dot productive column. R equals to 2p plus 2q. But the second equation is the same. -8 minus 8, 4 is the same with the equation with coefficient 8, 8 minus 4. Is the same with the equation with coefficient 4, 4 minus 2. So the other two are redundant. So we have only one condition for the eigenvectors. So which eigenvectors can we find in this case? In this case, if R, the only condition is R equals to 2p plus 2q. That's the only condition. And of course, eigenvector is not 0. So PQR equals to, which is the projected eigenvector, P times something to be determined plus Q times something to be determined. Okay, so P, what is P? P, so look at P and Q like the two parameters, and R is expressed in terms of those parameters. So P equals to P. So P equals to P times 1 plus P times 0. Q is Q, so 0, 1 here. And R is 2P plus 2Q. So we got two eigenvectors for the corresponding eigenvalue lambda 1 equals to lambda 2 equals to 1, which at this moment you already know the matrix is diagonalizable. So that's the moment where you know that A is diagonalizable. So let's list eigenvectors. So for lambda 1 equals to lambda 2 equals to 1, we'll get V1 equals to 1, 0, 2, and V2 equals to 0, 1. Okay, so we are done with eigenvalues lambda 1 equals to lambda 2 equals to 1. Let's move to the remaining eigenvalues. Let's find the eigenvector for that one. So lambda 3 equals to -1. Now, exactly as before, we subtract -1 from the diagonal entries of A. So write the matrix A plus 1 times identity matrix. So -7 minus -1 is -7 plus 1. So -6, -8, 4, 8, 10. So now subtract, we add 1 to diagonal elements. 8, 10, -4, and then 4, 4, 0 times PQR to see what it is, the only condition is non-zero here, equals to null vector. So what does it mean? First of all, this is very important, that p plus q equals to 0. Then, or if you want, q equals to minus p. Right. Then this will be 8p plus 10q minus 4r equals to 0. And if we simplify by 2, we get 4p plus 5q minus 2r equals to 0. This will be minus, let's divide by 2 right away. So minus 3p minus 4q plus 2r equals to 0. Okay, so let's try to introduce q equals to minus p into those two equations, see what we get. The first one we get 3p plus 4p, so p plus 2r equals to 0. What about the second one? 4p minus 5p, so it's minus p minus 2r equals to 0, which is redundant. So the only conditions we have q equals to minus p from before, and p equals to minus 2r. So these are the only conditions to keep in mind. So let's write a non-zero vector pqr satisfying those. So p equals to minus 2r. Let's try to find everything in terms of r. Q equals to minus p, which will be 2r. We don't need this anymore. So once we got p equals to minus 2r and q equals to 2r, the vector pqr will be r times the vector minus 2, 2, 1. So p equals to minus 2r, q equals to 2r, r is r. So of course r is not 0 to be a genuine eigenvector. So we got an eigenvector for lambda 3 equals to 1, minus 2 to 1. So v3, the eigenvector for lambda 3 equals to 1, the minus 1 equals to minus 2 to 1. So we got 3 eigenvectors for a 3 by 3 matrix, which makes it diagonalizable. The diagonalizing matrix T is obtained by putting the eigenvectors a scala of the diagonalizing matrix. So the matrix with columns 1, 0, 2, 0, 1, 2, minus 2, 2, 1. Okay, so this matrix T satisfies A equals to D, P, D, T inverse. But to be able to calculate efficiently, we need to calculate the inverse. For this purpose, we execute the Gaussian elimination algorithm to find the inverse. So if you remember that algorithm, so we start with a configuration of 3 by 6 matrix in which to the left is T, to the right is identity matrix, and we do elementary operations to transform the left-hand side to identity. And then once we manage to do that, then on the right it will be the inverse of T. So finding T inverse now by using the Gaussian elimination algorithm. So write down T 1, 0, minus 2, 0, 1, 2, 2, 2, 1. But on the right we get identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Now we do a bunch of elementary row operations with the purpose to transform the left-hand side into the identity form, and to the right we will see the inverse of T. So let's learn how to do it. Okay, so let's try to first step is to create zeros. We use pivots to create zeros below and move from left to right. So multiply the first row by minus 2, create the third row. If you do this, the first row remains the same, and the second row remains the same. 1, 0, minus 2, bar 1, 0, 0, and then 0, 1, 2, 0, 1, 0, and then 0, 2, 5, then minus 2, 0, 1. Okay, then this will be the new pivot and create zeros below. We get multiply the second row by minus 2 in the third row. So what we get here, the first and second rows remain the same. So 1, 0, minus 2, bar 1, 0, 0, 0, 1, 2, 0, 1, 0, and 0, 0, 1, 0, 0, 1. We get then minus 2, and a 1. Next, this will be the pivot, and now it's about time to create zeros above and move from right to left if necessary with those pivots. So let's multiply the third row by minus 2 in the second row, and the third row by 2 and in the first row. If we do this, above this one we got zeros, so we managed to create identity matrix on the left. I'll not write it, so I'll just say you will get identity matrix I3 here, and see what we get on the right. If we do those two elementary row operations, the last row remains the same, minus 2, 1, after the bar. Okay, now let's see. Multiply the third row by minus 2 in the second row. So I get here a 4. We get a 5. And then we get a minus 2. Then multiply the third row by 2 and make the first row. So we'll get minus 3, minus 4, and 2. So this will be, according to this algorithm, the inverse of t. So let's try to keep the fruit of the work and erase the work. So finding t minus 1, t inverse, we got this. So let's put the next so t inverse will be minus 3, minus 4, 2, 4, 5, minus 2, minus 2, minus 2, 1. Okay, so well, just in case we need to just verify. So t inverse times t, first row, first column, we need to get a 1. So minus 3 z plus 0 plus 4 is a 1. First second, we get minus 4 plus 4 is a 0, but it should be. First third, we get a minus 6 plus 8 plus, so minus 6, minus 6, no, 6 minus 8 plus 2 is a 0. And then second, first, 4 plus 0 minus 4 is a 0. Second, 5 minus 4 is a 1, as it should be. And second, third, we get minus 8 plus 10 minus 2, that's a 0. Third, first, we get a minus 2 plus 2 is a 0. Third, second, is minus 2 plus 2 is 0. Third, 4 minus 4 plus 1 is a 1. So yeah, that's okay, that's just in case. We always is good to verify what we do. So just to be sure at the end of the program we do test. So now let's try to write down the only what we really need. So okay, so at this moment we got the following. We got d equals to 1, 1, minus 1, 0, 0, 0, 0, 0, 0. T equals to this one, and T inverse is this one. Let's put it here. T equals to 1, 0, minus 2, 0, 1, 2, 2, 2, 1. And T inverse is minus 3, minus 4, 2, minus 3, minus 4, 2, 4, 5, minus 2, and minus 2, minus 2, 1. Okay, now let's do applications. We diagonalize the matrix. We already know that A equals to T d T inverse. Let's do the first application. Find the explicit formula for A to the power n. By using the functional calculus formula we discussed in class, A to the power n is shifted to D. So basically the T d to the power n T inverse, which will be 1, 0, minus 2, 0, 1, 2, 2 to 1. Let's see. D to the power n is 1, 0, 0. So 1 to the power n. Then put 1 to the power n, 0, 0, 0. 1 to the power n, 0, 0, 0, minus 1 to the power n. Times T inverse, which will be minus 3, minus 4, 2, 4, 5, minus 2, minus 2, minus 2, 1. So 1 to the power n is 1. Let's keep the 1s here, and then minus 1 to the power n. Okay, now let's calculate the product of those three matrices in this order. So as we know that matrix product is non-commutative, so we have to be cautious about don't change the order. So let's multiply those two. And then the result is multiplied from the left to this one. Okay, so let's see what we get. First, minus 3, minus 4, 2. Second, first, second, third row, dot column. So 4, 5, minus 2. And then minus 2 times minus 1 to the power n, minus 2 times minus 1 to the power n, and then minus 1 to the power n. Then we have to multiply in the end this one with this one. This one on the left, this one on the right. So what will be the result? So that's the end part of the matrix. Okay, minus 3 plus 4 times minus 1 to the power n. Minus 3 plus 4 times minus 1 to the power n. That's first. First row dot product with first column. So minus 3 plus 4 times minus 1 to the power n. Okay, first, second is minus 4 plus 4 times minus 1 to the power n. Minus 4 plus 4 times minus 1 to the power n. And first, third, we get 2 minus 2 times minus 1 to the power n. So we got the first row of the matrix A to the power n. That's exactly the first row. So second first. So second dot product with first row is 4 minus 4 times minus 1 to the power n. Second is 5 minus 4 times minus 1 to the power n. And second, third, we get minus 2 plus 2 times minus 1 to the power n. So minus 2 plus 2 times minus 1 to the power n. Finally, third first. Third first is minus 6 plus 8, that will be a 2. 2 minus 2 times minus 1 to the power n. Okay, then third, second, we get a minus 8 plus 10, that's a 2 minus 2 times minus 1 to the power n. And third is 2, so 4 minus 4 is a 0, just minus 1 to the power n. So there's the final result as of the nth power of the matrix n. So this will be the a to the power n. It was obtained by using this procedure of diagonalization. Okay, the next application involves calculating the matrix exponential and solve a linear system. I will give the linear system later after we solve exponential of at. For the exponential of at, we apply the same principle of functional calculus we discussed in class. So number 3 here, exponential of at will be t times exponential of dt times t inverse. Right? What's exponential of dt? Exponential on the diagonal matrix, and on the diagonal exponential of the first eigenvalue t times then exponential of the second eigenvalue times t, then exponential of the third eigenvalue times t. So this will be t 1 0 minus 2 0 1 2 2 2 1. That's a t. Let's do exponential of dt. D is 1 1 minus 1 on the diagonal. Exponential of dt will be e to the power t e to the power t e to the minus t on the diagonal, because d is 1 1 minus 1. Exponential of dt will get e to the power t e to the power t e to the minus t. Then 0 is inverse because it's diagonal. So t exponential of dt, right, that's t exponential of dt times t inverse, which again copy that one. So minus 3 minus 4 2 4 5 minus 2 minus 2 minus 2 and 1. So, okay, so t exponential of dt times t inverse is exponential of at. As before, let's calculate the product of these two and then multiply the resulting matrix here on the left by t. So this one will be first minus 3 e to the power t minus 4 e to the power t 2 e to the power t 4 e to the power t 5 e to the power t minus 2 e to the power t. Then minus 2 e to the minus t. Then minus 2 e to the minus t. Then e to the minus t. Then multiply this one on the left with this one on the right. So let's see. Okay, so let's try to add some space here. Let's keep exponential of at equals so multiply the product of these two. On the left this one, on the right the other one. Okay, so let's do first row, first column. We'll get minus 3 e to the power t plus 4 e to the minus 3. So minus 3 e to the power t plus 4 e to the minus 3. Okay, for second. Minus 4 e to the power t plus 4 e to the minus t. So minus 4 e to the power t plus 4 e to the minus t. Right? First third. We get 2 e to the power t minus 2 e to the minus t. Second first. We get 4 e to the power t minus 4 e to the minus t. Second. 5 e to the power t minus 4 e to the minus t. second, third. We get minus 2 e to the power t minus 2 e to the power t plus 2 e to the minus t. Third first. Okay, so let's see what we get here. 2 to 1 is the third here. So minus 6 e to the power t plus 8 e to the power t is 2 e to the power t minus 2 e to the minus t. Third, second. Minus 8 e to the power t plus 10 e to the power t together is 2 e to the power t minus 2 e to the minus t. Third. 4 e to the power t minus 4 e to the power t is 0, and just e to the minus t here on the lower right corner. So this will be exponential of 8t. Now, let's solve a system of linear differential equations induced by that matrix A. So the system will be, as a byproduct of the calculation of the exponential, we'll keep it here. Let's solve the system of linear differential equations. X1 prime equals to, use the first row as the first row of the coefficient matrix, equals to minus 7x1 minus 8x2 plus 4x3. X2 prime equals to 8x1 plus 9x2 minus 4x3, and x3 prime equals to 4x1 plus 4x2 minus x3. Okay, since we got here, let's put very simple initial conditions. We don't have it very much. x1 of 0 equals to x2 of 0 equals to x3 of 0 equals to 1. Okay, so as we discussed in class, so if we calculate the exponential of the matrix A times T, the solution of such a linear system is x1, x2, x3 is exponential of AT multiplied by the vector of initial conditions. Matrix exponential times the vector of initial conditions, 1, 1, 1. Okay, so we have to multiply this matrix by the column matrix 1, 1, 1. So x1, x2, x3 will be. So let's try to write down the result. Okay, so we want to multiply this matrix by 1, 1, 1. Okay, let's do first dot product is 1, 1, 1. So let's see. We get the sum of all the entries, basically the sum of the entries in the first row. So how many e to the power t's we got? Minus 3 e to the power t minus 4 e to the power t. So far we got minus 7 e to the power t plus 2 e to the power t minus 5 e to the power t. How many e to the minus t's we got? 4, another 4 minus 2 plus 6 e to the minus t. What about x2? We have to multiply the second row times the column vector 1, 1, 1. This is the sum of the entries of the second row. Let's see how many. Let's count the e to the power t's. 4 of them, 5 of them, minus 2 of them is 7 e to the power t. Let's count the e to the minus t's now. Minus 4, so far is minus 8, plus 2 is minus 6 e to the power minus t. Which is always keep an eye on the initial conditions. At 0 we must get 1. So at 0 is set equal to 0, 7 minus 6 is 1. So that's okay. Then third first multiply the dot product with the third row and the column 1, 1, 1, which in fact the sum of the entries on the third row. Let's see how many e to the power t's we got. 2 e to the power t, 2 e to the power t, that's 4 e to the power t. Minus 2 e to the minus t minus 2 e to the minus t, so minus 3 e to the minus t. That's the x3. So basically we got x1 of t, the solution of the linear system, x1 of t equals to minus 5 e to the power t plus 6 e to the minus t. x2 of t equals to 7 e to the power t minus 6 e to the minus t. And finally, x3 of t equals to 4 e to the power t minus 3 e to the minus t. In other words, x1 is the first component of this vector. This is the vector exponential of at multiplied by the vector of initial conditions, which is 1, 1, 1. That's x2 here, that's x3 here, which are again listed at the bottom. So this would be the solution of the initial value problem. That's an IVP in the form of a system of linear differential equations with constant coefficients and with given initial conditions.